So today we're going to continue talking about estimating means with confidence intervals. So when we last left, we were talking about how to calculate a critical value with our calculators. And now we're going to get into the conditions for estimating means and how we check those. So again, something that's really important on the AP statistics exam is for you to understand why you're doing the math that you're doing and why you're doing all these steps and why they're important to check so that you know that your statistic is valid and a true estimate. So the first condition that we check is random, right? And again, this stuff might be stuff you might not need to write down, stuff that you might already know. I just am re-emphasizing for the 6,000th time because this is important. The random condition is crucial for doing inference. If the data doesn't come from a random sample, you can't draw a conclusion about a larger population. So you need to make sure that you have a random sample. The random condition really checks to see if your stat is good. The next thing that we need to do is when and only, like if and only if you are sampling without replacement, you need to check the 10% condition. And this ensures that our formula for the standard deviation is approximately correct. If we start to grab a sample size that's too large without replacement, that is going to change the variability from sample to sample, and our standard deviation will change. So we have to check the 10% condition to make sure that our formula for standard deviation is correct. And then last but not least, you've been in, for the past 2 chapters, we've been doing large counts. But now what we're going to do is something called the normal condition is what I call it. So instead of RIL, with the 10% being the I, or independence is the other thing it's called, I think of it as RIN. So now I'm checking the normal condition to ensure that it's appropriate to use a t-distribution to calculate the critical t value. Okay, and I bet you're thinking to yourselves, normal condition, how do we check her again? And that's just, is the sample size greater than 30, greater than or equal to 30? So let's look at that again. So the conditions, again, random. These are the conditions that we have to check when we're doing this. Random, that it comes from a random sample. 10% when we're sampling without replacement. And then normal. There's a couple of ways that we can check the normal distribution. So the first is if they tell us that the population is normal. Guess what? If the population is normal, so is the sample, irregardless. So if the population is normal, our sampling distribution is going to be normal. So if I'm told it's normal, I don't have to look for anything else other than that. If I'm not told that it's normal, or they don't mention anything about whether or not the population distribution, what it looks like, then I have to look and see, is the sample size large? And large means, is it greater than or equal to 30? If it's greater than or equal to 30, then we're approximating normal, and we can say, okay, yeah, we can follow one of these distributions. So if the population distribution has an unknown shape and n is less than 30, then we have something that we need to think about, okay? So we said that we use the t-distribution for smaller sample sizes, but here, Ms. Shope, you're telling us we can't use sample sizes of less than 30. You can actually, but there's another check. So if the population distribution has an unknown shape, like I don't know if it's normal or not, and the sample size is less than 30, so I don't get that first check, I don't get that second check, I can use a graph of the sample data to assess the normality of the population. Okay, and I'm going to explain this further in a little bit. And we do not use t-procedures if the graph shows a strong skew or any outliers. Okay, so we do not use a t-procedure if the graph shows strong skew or outliers. Like, how does this work? Why strong skew and outliers? Why do we have to look out for them? Well, there's a specific reason. So I have to teach you about this word called robust. So an inference procedure is called robust if the probability calculations involved in the procedure remain fairly accurate when a condition for using the procedure is violated. Okay, so it's robust if the probability calculations involved in the procedure are fairly accurate when a condition is violated. You're probably like, what? So in English, a CI confidence interval is robust against a non-normal distribution. Again, what does that mean in English? That means that the confidence interval is still pretty accurate, even if the distribution isn't normal. In other translation words, what does that mean? It means approximately 95% of many confidence intervals contain the mean if I'm doing a 95% confidence level. Okay, so that's nice. I can do this even if it isn't normal? Okay, as long as, right, we look out for these things. So a confidence interval is not robust when there are outliers or when there is a strong skew, meaning that the confidence interval is not accurate anymore. So to sum up all of this weird stuff with robust, basically it means that, look, if you have a sample size less than 30, but hey, there's no outliers and it's not strongly skewed, you're okay. You can still use it because it's probably approximately 95% of the confidence intervals are going to contain the mean if you're doing a 95% confidence level. So it's okay, still use it, it's fine. But if it's less than 30 and there are outliers or it is strongly skewed, you cannot use it. So, okay, let's go back to the conditions. So, conditions for using T procedures. If it hasn't told us anything about normal, and we have a sample size of less than 30. So if the sample size is less than 30, use T procedures if the data appear close to normal. So what are you looking for that? And close to normal is a really relative term, right? I want roughly symmetrical, one peak or close to one peak, and no outliers. Do not use the T if you see a large skew or any outliers. To prove this, you must draw a graph for this. It needs to be a histogram or a dot plot. Okay, now it doesn't have to be perfect, but you need to draw something showing that you've looked at the distribution. Okay, now if the sample size is at least 30 and it's skewed, I don't care, it's 30. So it's like step one is, does it say that the population is normal? Yes, proceed. No? Okay, let's see. Is the sample size larger or equal to 30? Yes, then proceed. We don't care what the distribution looks like. No? Then we need to draw a pretty picture of the graph, looking at a histogram or a dot plot to see, is it approximately normal? Is it close to normal? So let's try it. Okay, so here's one. Determine if the normal or large sample size condition is met in each of the following settings. So here's A. We want to estimate the average GPA of students at your school. You randomly select 50 students. Here is a histogram of their GPAs. Okay. To your neighbor friend, is the large sample, normal or large sample condition met? How do you know? Go ahead and pause the video so you can talk to your neighbor friend. Okay, and coming back. So, is it normal? The sample size is 50, which is greater than 30. So we're good. I didn't even need this beautiful little histogram here. I'm good. Let's try another. Determine if the normal or large sample size condition is met in each of the followings. Oh, look at that. Look at that stem and leaf plot. We haven't seen those in a while. So B, how much force does it take to pull wood apart? The stem plot shows the force in pounds required to pull a piece of dug fir apart for each of 20 randomly selected pieces. Talking to your neighbor friend, is the normal condition met? Go ahead and pause the video to talk. Okay, and coming back. So looking at this, they've told me my sample size is 20. So, I got to look at this distribution. And remember, with stem and leaf plots, I got to turn my head and look at it on the side. And if I do, I see, oh my God, it's so skewed to the left. No, the stem plot is strongly skewed to the left with possible low outliers because that's really far from the rest. And N is 20, which is less than 30. Let's try another. Suppose you want to estimate the mean SAT math score at a large high school. Here's the box plot of SAT math scores for a random sample of 20 students at the school. Okay, so normally the AP exam says, please, oh, please, oh, please, don't use box plots for this, but they've given you a box plot. So there we go. Thinking about what a box plot looks like, talking to your neighbor friend is the normal condition met. Go ahead and pause the video. Okay, and coming back. Even though 20 is less than 30, the box plot is only moderately skewed to the right and there's no outliers. Again, skewed to the right because if you look at the right-hand side, the quartile 4, that line is a little bit larger than the quartile 3 line, or quartile 1 line. So yeah, your whisker, if you will, on your right side is a little bit bigger, so it's moderately skewed, but it's not strong. So, nope, we can still do it. We are going to try a state plan do conclude for a confidence interval for mu. Yep, we're doing it. So, I need you to get out a TI-84. And we're going to go through this. So, the problem is, a manufacturer of high-resolution video terminals must control the tension on the mesh of fine wires that lies behind the surface of the viewing screen. Too much tension will tear the mesh. Too little will allow for wrinkles. The tension is measured by an electrical device with output readings in millivolts. Some variation is inherent in the production process. Here are the tension readings from a random sample of 20 screens from a single day's production. Construct and interpret a 90% confidence interval for the mean tension mu of all the screens produced on this day. Now, to start this off, I am going to have to enter all of these numbers into a list, right? Because I'm going to need a mean, and I don't want to do it by hand. So what I'm going to do is on the next slide, I'm going to show you me entering the numbers in the calculator, and then I'll bring this screen back so that in case you missed one, you can enter the numbers as well. All right, so I'm entering the numbers, so I'm going to my stats, and then I'm going to hit edit. So I press stat and edit, and I should see all my lists. So list 1 looks kind of boring, so I'm going to go ahead and hit clear up at the top there. So it says list 1 equals blank and hit enter. So now that's cleared. So I can go ahead and enter in my data. So I had, and I'll read the numbers out loud if that helps, so that you can enter into your calculator as well. I have 269.5. I have 297.0. I have 269.6. I have 283.3. I have 304.8. I have 280.4. I have 233.5. I have 257.4. I have 317.5. 327.4. Halfway there. 264.7. 307.7. 310.0. 343.3. 328.1. 342.6. 338.8. 340.1. 374.6. 336.1. And I should be left, if I've entered in 20 values, which is always my quick check, I should see L1 equals 21, meaning I want to enter in the 21st number. So that means I have 20 numbers entered in. And I'm just going to do a quick check to make sure they all have 3 to 4 digits, and they do. So I think I am good there. What comes next? Well, I want the mean to this. So I'm going to need to go stats, calculate 1-bar stat. Right? And this time I put mine in L1, so I'm going to have to hit second and 1 because mine was L1 and there was no frequency. So I'm going to clear that and calculate. And there's my X bar and there's my S of X, which is what I want. I'm going to need my S of X later. Right? So my X bar and my S of X are right there. Just in case you needed the numbers again, here are the numbers just blown up a little bit more. If you need just one more second to get all of those numbers into your calculator and just practicing how to do a list. If you need to pause the video, go ahead and do that. Okay, so because this is our first state plan do conclude with mu, I will kind of walk you through this one, but maybe you could just think in your head how you would do this. So problem, construct and interpret a 90% confidence interval for the mean tension mu of all the screens produced on this day. So we're going to start with our state. And remember, we've said like we wish to find, or you could just say a 90%, you could just start with the word 90% confidence interval for mu, and then you need to define what mu is, right? So 90% confidence interval for mu equals the true tension of all video terminals produced that day. Perfect. Okay, plan. Plan would be the next step. So think in your mind, what is the name of that inference method, right? So this is a one sample T interval for mu, right? Because we have one sample, but now it's not Z, it's T, and it's an interval, and it's for mu. This is why I was so specific about you guys saying, like, when you were saying one sample, and you didn't say if it was for P or mu or whatever, right? So we need to say that it's a one sample T interval for mu. And then we've got to check our conditions. So random, the random sample of 20 screens produced that day, great. 10%, assume that 20 is less than 10%, or I would have said there are more than 200 video terminals that are produced in a day. And then normal, since it's less than 20, I would draw a dot plot. And dot plot usually, if it's less than 30, dot plot, right, is a pretty easy one to do. So that tends to be my go-to is a dot plot. So the dot plot doesn't show any strong skew or outliers. And you might look at this and be like, well, I don't see a peak in the center. Right? Yeah, of course not. These drawings are not going to be perfect. They're meant to be like they're going to be really obvious if they are strongly skewed or there is an outlier. So for the most part, this should be okay, but if you start to see something really weird, like it's going to be very obvious if it violates a condition. Okay, so we're good for the state and we're good for the plan. For the do part of this, again, I would have entered all the numbers in, and I entered in my X bar and my S of X. So I would have said that, like, my X bar is this, my S of X is this, and I would have gotten it from my calculator, just straight up. Then I need to have, and this is new, I need to state my degrees of freedom. So I need to say degrees of freedom is 19. My critical value is 1.729. So where did we get that? Let's look into that. So I knew that the sample size is 20. 20 minus 1 is 19, so I have 19 degrees of freedom. That always has to be stated in your do, 19 degrees of freedom, because that changes everything. So I'm going to look here at 19 degrees of freedom, and I'm going to look at confidence level. I actually go to the bottom first and usually go to 90% confidence level, and I'm going to look up until I get to 19, and there it is right here, 1.729. Not that you can see this because it's super, super tiny, but if you have a blue book, you can look up 90 at the bottom and you go up until you get to 19, and where they cross right here is our critical value. Okay, so I have notice I've written my degrees of freedom. We now talked about where the 1.729 comes from here for the critical value. And now let's look at this equation here. So here is my mean, and this is my sample mean, my X bar, 306.23, plus or minus my critical T, 1.729. And then here's my sample standard deviation, right? S of X, 36.21, divided by the square root of my sample size, 20. And then we came up with an interval here. Okay, now we're on to the conclude. We are 90% confident that the interval from 292.32 millivolts to 320.32 millivolts captures the true mean tension in the entire batch of video terminals produced that day. That is how we do a state plan can do for confidence interval for mu. Again, real similar to the other state plan do concludes we've done before. We're just adding this thing with degrees of freedom and critical value. And you're probably saying, Ms. Shope, you didn't do a distribution. That's because I didn't do a z-score or a, get ready for this, t-score. I just did a critical value. So I don't need to draw the pretty distribution. All right, so the last thing I wanted to talk about is just a little bit more about the margin of error and things that affect the margin of error. So in Chapter 8, which again was first semester, we learned about how different factors affect the margin of error when calculating a confidence interval for a population proportion. The lessons are the same, so sum it up. The margin of error decreases as sample sizes increases, assuming that the confidence level and standard deviation remain the same. This makes sense. Margin of error goes down the more the sample size goes up, because the more the sample size goes up, the more sure we are of the values, the less variability we have, and so therefore margin of error goes down. The margin of error is proportional to 1 divided by square root of n. So quadrupling the sample size will cut the margin of error in half, assuming that everything else remains the same. So this is important to know if you ever want to know the proportions. I feel like every so often there is a strange question on the AP exam that asks you, hey, if I increase the sample size by 16 times, what will that do to the margin of error, right? So thinking about it, that we're thinking about how this works in proportion. And then the margin of error will be larger for higher confidence intervals, right? This makes sense, as wider intervals will have a greater capture rate than narrow intervals. So if I have a higher confidence level, I have a super wide margin of error, right? That makes sense because it just captures more things. And then the margin of error never accounts for bias in the data collection process, only sampling variability. So the margin of error does not account for the fact that you messed up in your wording, or that you missed some people in your sample, or you left out a certain population. That won't account for, margin of error doesn't account for that. It literally only accounts for the fact that I can grab a random sample and have one random sample be completely different from another random sample. All right, so that is it for this section, and then you can start working on your homework. And obviously I didn't collect homework today, so what was due today and what is due Monday, I will collect on Monday. Have a great weekend.